Thank you for being here today. I will demonstrate how the gap between inquisitive investigator and the data describing the phenomena they wish to explore is reduced and the workflow simplified with OGC data interoperability and a new abstract digital Earth spatial reference standard called a Discrete Global Grid System. A DGGS is not a navigation grid. It is a data-agnostic information grid. Answering where is it and what is here is as easy as a spreadsheet. Enter data values, use expressions to calculate new values, search by selecting and refining, and explore unaggregated spatial statistics. Its nested equal area cells store data values from any geospatial data source, Earth observations, spatial statistics, and conventional GIS features. The richest sources of data values are either the attribute values from vector features, rivers and lakes extracted here from the joint NRCan and USGS North America Atlas, or data values stored as coverages. The data values used in this demo are accessed through OGC's web feature services and web coverage services. I'm connecting to the NGA Arctic Surface Elevation Model web coverage service by pasting the Get Capabilities URL from the Arctic DEM user guide. Standards of interoperability make it simple to discover, access, and use data. The DGGS integrates and fuses the data values on the fly for visualization, analysis, and modeling. I am exploring the web coverage service from the Socio-Economic Data and Applications Center of the Center for International Earth Science Information Network at Columbia University. There are a lot of data values here. I will connect to the global population density coverage to integrate into our study area. CDAC is one of the distributed active archive centers of the U.S. National Aeronautics and Space Administration. Integrating spatial statistics with Earth observations is a powerful utility. The Pyxis Studio exposes 5 methods for selecting an area of interest. Pick a spot on the ground, select a vector feature, draw freehand or a polygon, or calculate a drainage area from the best elevation available. Let's start by exploring Alaska. The DGGS is very efficient at aggregating all the data values stored in the equal area cells and reporting it here in the legend. I can refine the selection by adjusting any range of values. The spatial statistics are automatically regenerated for the updated selection. One of the key advantages of a DGGS is selection of ad hoc areas for analysis over multiple sources of data. I want to know what is going on in my area of interest right now, so I'm requesting current real-time temperature and snowfall from Unidata's Atmospheric Data Service. It's as easy as dropping the data request into the search bar. OGC is exploring new ways to add scientific atmospheric data models to the WCS specification. The Pyxis Studio allows metadata to be read and used. In this case, we can see the temperature is in degrees Kelvin. That's easily remedied if we want to convert the data to Celsius. With data normalized in the cells of the DGGS, we can use algebraic expressions to add more data to the grid. Operations on DGGS values is an intuitive way to do analysis and modeling. We can explore the individual data values stored in the infinitesimal cells by picking points on the globe. Here are all the attributes we are monitoring, including the new temperature in degrees Celsius. Data providers can facilitate data discovery through the organization of data into a catalog. OGC Web Catalog Standard, CSW, was used by GMU and CompuSalt during the Arctic Spatial Data Pilot Project. I am choosing some wildlife feature data developed by the International Union for the Conservation of Nature and the Conservation of Arctic Flora and Fauna of the Arctic Council. There's just so much data we can get. There are other ways to discover data too. Interoperability standards allows Pyxis to crawl the web for data of interest. An important data source for our analysis is the Circum-Arctic Map of Permafrost from the National Snow and Ice Data Center, another NASA DAC. I'm grateful to have the United States support access to these critically important data repositories. There are a few others that match this common good. NatureServe has provided access to a multitude of climate models. We will use mean temperature models to develop a time series of potential climate change. We can use this data to do some analysis. If we select an area of northern Canada and refine the selection based on current mean temperature, we observe that the permafrost tends to form below -4 degrees Celsius. The same is true in Alaska, with some exceptions. A localized phenomena is accelerating the formation of permafrost in this valley. The Mackenzie River Basin is automatically delineated using the elevation data values in the DGGS. The DGGS aggregates the data values within the selected area and reports spatial information within the watershed. The Mackenzie River Basin is an important corridor that connects Canada's northern communities to the south. It has traditionally been the land that funneled humans into the Americas. Today, resource extraction and wildlife coexist. Traditional ways with new technologies promise to mitigate loss. We can use temperature change time series to visualize and report on the possible receding permafrost. I've added several feature data sources describing infrastructure in the north. Refining the polygon selection on current and possible future temperature results in an area of interest that may experience permafrost loss. The location and names of the infrastructure affected is listed in the legend.